Thank you very much. And thank you for the invitation. Very happy to be here and seeing all of you. Yes, this is joint work with Jason Gaitan at Cornell, Ying-Kai Lee at Northwestern, Barlight and Alex Lipkins at MSR. This was done while Jason and Ying-Kai were interns at MSR over the summer. I want to note that Ying-Kai is on the market this year and he's fantastic, so you keep an eye out. And I should also mention this is work in progress. And so, very happy to have any feedback. Please feel free to interrupt me with questions at any time. So this talk is about online advertising. Okay, it's just an algorithmic game theory seminar. Let's go back to the classics. All right, so this is monetization of the internet. I want to think about like sponsored search, basically. Okay, so you type a keyword into Bing, you get ads, or since the 10 years since I took that screenshot, you have ads embedded in operating systems, ads like mobile ads, lots of different contexts, and getting lots of monetization in lots of different ways. Okay, and so as many of you already know, these ads are sold by auction. Okay, so every impression, what happens in the back end is an auction is run to figure out which ads get shown and how much they pay. And so if I'm an advertiser, I want to participate, I have to set up what's called a bidding campaign that will basically bid automatically on my behalf inside these auctions. And these campaigns can be relatively complicated, right? So I can set bids. They vary by keyword. They vary things like demographics of the people who are looking at them, and so on. And I can also specify a budget that binds over the course of some period of time. So I can say something like, here's how maximum amount I want to spend over, say, a day. Okay, so it's a campaign. And there are lots of advantages to sort of running auctions this way instead of having people buy the ad space directly. But a downside is that managing these campaigns turns out to be very complex for a bunch of reasons. One of which is that the actual details of the auction running in the background can be a little bit finicky and can vary by the actual context. And so usually one campaign is feeding into lots of different channels by which these ads are being shown. And so the details of the auction can be a little funny, especially when you have different ad formats. But even if the underlying auctions were, say, truthful and simple, like even if they were, say, second price auctions, the fact that I have this budget that's binding over the course of many auction instances would still make bidding somewhat complicated, right? So even if I had second price auction in the background, it's still not a truthful auction in the sense that I have to think about my budget and how to sort of optimally allocate it across time. Okay, and so setting up my campaign sort of properly spread my budget around is a non-trivial task, even if the auctions underneath were simple, which actually they're not. Okay, and so this complexity led to the rise of a few things. First of all, sort of back in the day, a lot of advertisers, especially big advertisers, would use third-party optimizers to sort of run their campaigns for them. And eventually this led to the observation that the complexity of the underlying auction maybe actually isn't so important because advertiser incentives don't bind at the level of an individual auction instance. Okay, I get millions of auctions over the course of the day. I don't care so much what happens in an individual auction. What I care about is over the course of the whole day, how much did I spend and what did I get for that money? And so ultimately, this led to the development of what's called auto bidders, where you have a relationship where the advertiser specifies not the fiddly details of the campaign, but rather high-level constraints and objectives, right? So for example, they'd say, here's how much I want to spend. Here's the maximum amount I'd be willing to spend on individual keywords. Please, maximize value subject to those constraints, right? And so it would specify that to a bidding agent, an algorithm that now has a mandate to attempt to do that on the behalf of the advertiser. And that automated bidder now places bids in the individual auctions, attempting to follow those instructions. Okay, and oftentimes those bidders actually sit inside the platform itself, which is beneficial because then it gets access to all these extra signals that the platform has to help it with this task. So oftentimes it's sold as like there's machine learning under the hood. It can sort of dynamically adapt its bids over time in response to what it's observing from the auctions. The advertiser in some sense is sort of agnostic to what it is the automated bidder is doing. It's just that at the end of the day, the bidder will then come back with a report that says, here's how much you spent, and here's your aggregate result in terms of like number of impressions or number of clicks or what have you.
But then
Yeah.
towards the end of the day means that if your budget is spent, maybe you're going to be out, or maybe you have lots of extra money, and others can take advantage of that.
Exactly. Exactly.
If you know when the end of the day is for each person, which again may depend on the clock or whatever in different regions or so on, but there may be some things happening then, no?
Yes. So these are exactly the kind of details that hopefully sort of get shoved into the automated bidder itself. And so in particular, I guess I'll get into the modeling in a second. When we talk about things like budget per day, typically this is like, over the course of I have a certain rate at which I want to spend. But really the automated bidder, if I say something like, oh, it's between midnight and midnight, the automated bidder should be tuning itself to make sure that it sort of does a soft landing and actually spreads its budget properly around the time. Yeah, exactly. Okay. So I just want to say about this automated bidding was extremely successful and is extremely popular. Okay, so here are screenshots of the interfaces from a bunch of different platforms. They've got Bing here, Google, Facebook, third party as well. An increasing fraction of traffic goes through these, to the point where for some platforms, actually they don't even support this manual bidding anymore, right? Really all your traffic goes through these these automated bidding campaign managers, okay? And this raises some questions. In particular, like we can sort of imagine what I would do to design like an individual bidder working on behalf of an advertiser. But if all the traffic is going through these auto bidders, we might ask what the impact is on sort of aggregate market outcomes, right? So if everything's going through these bidders and they're running some machine learning methods under the hood, am I going to converge to a market equilibrium? That'd be nice. Am I going to like do price discovery and sort of get the right prices? Or are they going to do something funny and like implicitly collude and go off into some crazy part of the space? And moreover, how sensitive is this to the choice of auction that's being run sort of deep under the hood, right? So some engineer going to say, oh, they're going to like implement a new ad format with a new context and have some special auction to deal with that, and now suddenly everything breaks. Okay, so what we're going to do in this talk is we're going to be looking at a particularly simple method of actually running these auto bidders called adaptive budget pacing. And we're going to argue that when all the advertisers are running these things simultaneously, we get approximately optimal aggregate outcomes for the market in terms of efficiency. And this is robust to the choice of the auction that's being run in the background. Okay, so it runs for a variety of different auction formats. And then this last line is just saying that also these this particular way of doing budget pacing is like a reasonable thing for auto bidders to do, in that they still sort of respect the individual mandate of an advertiser in sort of like the single player version of the game. Okay, so this was very high level. To pin all this down and place it in the context of related work, there's like a ton of work on this. I want to give some details of the model and some examples, but just to foreshadow, let me just say a couple things about these different points. When I say that the auto bidding algorithm is simple, I mean like actually really simple. It's sort of this local memoryless thing. So there's no fancy RL going on here. Okay, and in fact, this is a method that's been studied previously. When I say approximately optimal outcomes, I'm going to be looking at aggregate efficiency, and the metric I'm going to be looking at is liquid welfare. If you don't know what that is, that's fine. I'll explain in a little bit. When I say variety of auction formats, the actual condition I need is that my underlying auction is a core auction. It's generating auction, outcomes in the core, and also satisfies a certain monotonicity property I'll talk about. If you don't know what all that is, that's fine. Really, it includes second price auctions, first price auctions, and GSP auctions, and other sort of natural auctions that get used in this context. Good, and as I said before, this last thing about getting low regret for single advertiser, I basically just mean like a stochastic single player environment. For these different types of auctions, this simple method actually does well, and perhaps better than one should expect it should. And just a technical point, you might imagine like one way you could prove an argument like this is to say, oh, I converge to equilibrium, and then you get like a price of anarchy type of result. Actually, our analysis approach is not going to rely on these auto bidders actually converging to any equilibrium. And in fact, there's good reason to think that they might not due to computational hardness issues. Okay, so this is all just foreshadowing what's coming up. Let me now talk about the model. Okay, so I want to imagine that there's T rounds. Okay, T is known, and there's going to be one impression auctioned off each round. There's going to be N advertisers, and each advertiser has its associated auto bidder. And the protagonist in the story is going to be the auto bidders themselves. Okay, so the auto bidders are getting instructions from the advertisers. And the particular format of auto bidder I'm going to be thinking about is one in which the advertiser says, here's my total budget, and here's some values or maximum bids. And these are constraints on what the auto bidder can do and how much they can spend. Then in each round, these values or maximum bids are going to be drawn from some distribution. And I want to think of this as something like the impression has a type, right? It's the demographic and the keyword and all of this. And these values are sort of dependent on that type. And so importantly, these can be correlated across the advertisers. And this is crucial. Okay. So it's not that each value is being drawn independently from some distribution, but rather I have a vector that's being drawn each round from some distribution.
But F does not have a subscript T, which means all periods are the same. So those are IID over periods.
It's IID over time. Yes, exactly. But correlated across the advertiser. So it's, I'm imagining that there's a distribution over the types of impressions, and that distribution is not changing over the course of a day. Okay. Then each round, the auto bidder gets to observe the realization of the value, and then places a bid, which by mandate is at most the value. And then the auction resolves. Okay. And notably, I'm not saying anything. Oh, yeah.
Brendan, yes, sorry. But that means that every second or every minute or whatever, you get the same kind of object, which is this realistic? Don't objects, don't you have, now it's this kind of car, now it's another type of car. You don't get the same object every period, no?
Good. So what I'm not capturing, so what I'm imagining each individual impression might be different. So I'm saying something like there's a certain rate at which 18 to 34-year-olds are searching for this query, and there's a certain rate at which 35 to 50-year-olds are searching for this query. And I'm assuming that those rates aren't changing over time. And so it's like every instant I'm getting a draw from, there's a certain chance it's 18 to 34 and a certain chance it's 35 to 50. What I'm not capturing here is this, if it's like in the morning, it's more likely that this type happens, and in the afternoon, it's more likely that type happens. If you wanted to capture that, you'd want to do this on a shorter time scale so that things are approximately uniform. Does that make sense? So I'm not assuming that all queries are 34 to 50 or 35 to 50-year-olds, rather that like the proportion is uniform across time. That's this distribution F.
But you are assuming IID F for over T, yes?
Yes.
Assume there is just so I is 1. Yes, forget the correlation inside. I don't care about. Take I as 1, just one advertiser. Yes. So you are saying that he's facing a stream of constant. So for him, every period there is a value from the same distribution. Yes.
Yes. I guess
for a specific keyword. Sergio,
for a specific keyword.
All of this is for a specific keyword. The same keyword is facing the same.
But keyword at 10 o'clock in the morning and the same keyword at 10 o'clock and 10 p.m. is a different thing. So you are assuming that throughout the day, you are facing all the time the same environment, which I think is not realistic. That's what I'm saying.
I want to make sure this is super clear. So the value is how much the advertiser spent. So the advertiser says something like, I'm going to bid up to $1 on watch. And but if it's like from an 18 to 34-year-old, make it, you can bid up to 80 cents. Okay. So suppose that's like what the advertiser has specified as the instruction. Okay. So they're saying it's like, if an 18 to 35-year-old queries, bid up to 80 cents. If a 35 to 50-year-old queries, bid up to $1. Okay. And so what's going to happen is over the course of the day, sometimes it's going to be 18 to 34-year-olds, and sometimes it's going to be 35 to 50-year-olds.
But will he know will he know whether it's this kind or that kind?
Yes.
But then it's not the same F.
No, it's the same. Sorry. the
There is an
value is
F1.
what's
There is an
the
F1.
value is what the value is what corresponds to the type. So every 18 to 34-year-old, my maximum bid is 80 cents. Let me go a little further and then get to an example, and maybe this will be more clear. Okay, so I don't want to think of the values as being like the F is just the fact that it's the uniform F is just saying that the distribution of who's coming doesn't change over time. That's all that this is. That's all this is saying.
Okay, I'm still have a, as I said,
let me move forward a couple. Let me move forward
Okay.
a couple slides, and then we'll come back to this and see if it still
Okay.
makes sense. Okay. So then so I make my bids, my auction resolves. My goal, so we're doing value maximization. So the goal is to maximize total value obtained, subject to the budget. Okay. Notice in particular, this isn't a utility assumption. I'm not assuming that the advertisers are value maximizers versus utility maximizers. This is just the mandate that's given to the auto bidder. Okay. So now the auto bidder has this thing it wants to do. How might it do it? Here's one particular thing that an auto bidder might do to translate these maximum bids into actual bids, all right, which is called budget pacing. All right, so remember the input is the budget and the maximum bids. The auto bidder maintains a shading factor, right? This is a particular way you do it. So you maintain a shading factor, which is basically how much you're going to reduce the maximum bid in order to get the real bid. I mean, this is going to be mu, and it's bigger than or equal to 1. And so in round T, the auto bidder is just going to bid the maximum bid divided by this mu. Okay, so if mu is 2, it means I'm going to take the maximum bid for that impression and divide it by 2, and that's going to be my bid. And importantly, I can adjust that mu over time as the auto bidder. Okay, so given my feedback, I can decide to make my mu higher or lower. Now, why would I want to do this? Okay, so this is a particular way to do auto bidding. Well, here's an observation. It turns out that if the underlying auction is truthful in the sense of quasi-linear bidders, then there is a choice of mu star, such that in hindsight, the optimal thing for the auto bidder to do is to just bid value over mu star every auction instance. Okay, this is optimal both for this mandate of maximizing value and also for maximizing the advertiser's utility. So these coincide. And the mu star you would choose is precisely the one that exhausts the budget over the course of the day. Right. And so this observation was actually one of the things that, like, one of the starting points of sort of auto bidding technologies, that originally these services were inside the platforms, particularly for the purpose of spreading budget. But then actually it turns out spreading budget is aligned with utility. Yes.
Now, optimal relative to what?
Optimal relative to the best profile of bids over the course of the entire history.
Which means like using a different mu every period T.
Yes, that would be like using a different mu every period T.
Brendan, a quick question. This mu is independent of I? It's mu T, not mu Ti.
Oh, sorry. Yes, mu I star. So for each auto bidder, this is what I'm writing here is for an individual auto bidder's perspective. So from the perspective of a particular auto bidder, it will be optimal in hindsight for them to do that's particular mu star, which should be mu star sub I.
Thanks.
And this is independent, so this doesn't rely on other auto bidders doing the same thing. So it's not an equilibrium result. It's like whatever other bidders are doing, this is always optimal in hindsight.
So,
And
Brendan, is this different than just saying what's the bid that you are going to bid next in the next round, depending on the history? How is it more restrictive using this shading factor than just saying what's the bid?
So the restriction here is that I'm choosing my bidding factor first before I observe the value. So remember, there's a distribution over what value I'm going to see. And I'm saying that no matter what I see, I'm going to bid that divided by this factor.
Okay. Got it. Thank you.
Yeah.
So now I want to understand, single round auction being truthful means that my optimal one period strategy is mu equal 1.
Exactly. Yes. So if there were no budget.
Okay.
Yeah, if there were no budget. Yeah.
If there were no budget, then I would want to use mu equal 1 every period.
Yes.
If there is budget, then what you are saying is, okay, let me just get the maximum proportion of optimal strategy. Okay, then it's just a shading by mu star that's given by the budget constraint. That's
exactly.
it.
Exactly. So this is an oft reproven result. And so I made some citations here. These are all proven in slightly different contexts and different levels of generality,
okay.
but it's the same idea.
You assume that everybody knows it. Some people don't. Sorry.
Yeah. Good.
For me, it's new, so I'm trying to understand it.
Yeah. No. So I mean, it's actually kind of a surprising result, which is why it's been proved a few times in the recent years. Okay. Good. Okay. So now I want to pin, like I just said a bunch of things. I want to pin it down with an example. Okay. So what's going on? So I want to imagine a scenario where I have two advertisers. Let's call them brand X and brand Y. They're both bidding on a keyword. Okay. Let's suppose they're both bidding on keyword watch. And they both say, oh, I have a daily budget. My budget is $50 per day. Okay. And the impressions are going to be sold by second price auction each round. Okay. Now I want to imagine that there's two different target demographics. Okay. Some of the impressions are coming from people that we think are age 18 to 34. Okay. And we expect there'll be about 100 of those per day. And the advertiser X says, those, I'd be willing to pay up to $2 to show my ad to those individuals. And advertiser Y said I'd be willing to pay up to $1 to send my ad to those folks. There's another demographic, which is age 35 to 50. Okay. Similar number of impressions per day, but the roles of the advertisers are flipped. Now advertiser Y says I'd be willing to pay up to $2 to show my ad to them. And advertiser X says I'd be willing to pay up to $1 to show my ad to them. Okay. Now, technically what I should be saying here is that there's 200 ads and each one is 50% one and 50% the other. I'm just going to, for the ease of making the example go through, I'll say, let's say there's 100 of one and 100 of the other. And so really you should think of this like an ex ante relaxation. You can imagine that what's really happening is this example is all subject to some noise that's going to be made small. Okay, so let's suppose I know there's going to be exactly 100 of one and 100 of the other. Okay, so what are the auto bidders going to do here? Well, one thing they could do is just not shade at all. They could just bid their value, they could just bid the specified maximum every round. Okay, in which case the bids are what's displayed here in green. In this case, because it's a second price auction each impression, every time the 18 to 34 comes in, bidder X is going to win and they pay $1, okay, which is the second highest bid. Similarly, every time the older demographic comes in, advertiser Y wins and they pay $1. Okay, in which case they each spend $100. Okay, oops, right? They were told, please don't spend more than $50, right? So this was not the right thing to do. But I mean, because it's a symmetric example, we can pretty easily see how I would fix this. Suppose that each shaded by a factor 2, which is to say they reduce their bids by half. Then the example would work out the same. X wins all the young, Y wins all the old, but they pay half as much because all the bids are half, and so the prices are half. In which case they would each spend 50.
Take a different budget for the two. That's not fair to give them the same budget. Give Y a different budget.
Okay, sure. So I guess this is a very simple example just for the sake of going through this. But I want to point out, so this is okay. So what am I saying? This is fine. This is an equilibrium, but it's not the only equilibrium. Okay, so this is, even for this simple example, that funny things can happen. So suppose that instead of this, advertiser X actually shades a lot and advertiser Y shades less. Okay, so X is going to bid lower each time. They're going to take the maximum divide by 3, and the Y is going to take the maximum divide by 1.5. Then what happens? Well, advertiser Y still wins all the old, and in fact, they pay less. Okay, this is this bottom row here. But now there's a tie on the young. Now, I haven't specified how tie breaking works, but let's imagine for some reason that advertiser X wins 75% of the time and Y wins 25% of the time. Let's not say why, but let's suppose that's what happened. Then it turns out that, Y wins all the old impressions at 33 cents each and 25 of the young impressions at 67 cents each. If I work out the math right, they spend exactly their budget, with this $50. And similarly, X spends $50. So this is also an equilibrium. Now there's a symmetric one where the roles of X and Y are reversed, and it turns out those are the only three equilibria in this particular example. Okay, now I said that you had this tie breaking that worked in this particular way. Why is that? Well, imagine, for example, that my auto bidders weren't just magically, doing this multiplier every time, but rather, I suppose I sort of started them around X around 3 and Y around 3/2, and then they were sort of looking at how their budget was tracking with my expected budget per round, and they maybe tweak their bids up a little bit if they're spending too little and tweak their bids down a little bit if they're spending too much. You might imagine that if I was sort of in this neighborhood, they would sort of be going up and down in a correct proportion to have their budgets track, which would track this particular notion of tie breaking. So there's a sense in which this is a sort of a stable outcome. And in fact, we could just draw that out. Okay, so what I've drawn here in this picture.
Brandon, but the difference between the first equilibrium and the other two, you said there are only 3, is the first one is efficient, the other two are not. Efficient in terms of the allocation.
Exactly. So I guess where I'm going with this is, since we have multiplicity of equilibria, we might care about how to compare those equilibria with respect to, say, efficiency. Interestingly, it turns out that the efficient equilibrium is not the stable one in this case. So what I've drawn in this picture is for every pair of like mu X, mu Y, if someone's overspending, then they're sort of moving their mu in the correct direction. And similarly, if they're underspending, I've actually plotted the 1 over mu X and 1 over mu Y just because the picture works out a little nicer that way. And you can sort of see from the picture that, first of all, you can sort of look at, here's where the 3 equilibria are. Those are the 3 equilibria that I described. This one in the middle is the one where they're each bidding a half. And it turns out that that's a bit knife edge. I'm not sure if you can see it from the picture. But actually, it's the other ones that are stable. And so in some sense, those are the ones that are more predictive in this particular example. Okay, so now is this exactly Sergio's question, right? So like, maybe now this is concerning. So sometimes maybe I get efficient outcome, maybe I don't get, sometimes I get an inefficient outcome. Am I concerned? So it turns out one can show there's always a pure Nash equilibrium in this game when the underlying auction is a second price auction. And it's known that at any such equilibrium, the resulting allocation is going to get at least half of the optimal liquid welfare. Okay, so there's basically a price of anarchy result in this context. So the Agarwal et al. Paper shows this for a class of constraints, includes these budget constraints, but also other types of constraints as well. The Babayoff et al. Paper shows this for a class of utility models that's not just sort of like linear up to a budget, but also like soft budgets and things like this. But regardless, this result is a special case of both.
Question. If the budget of one of the two, say in the example, is less than half of the other, does it kill the efficient equilibrium completely?
So this is why it's important that we're good. This is why we're talking about liquid welfare. So let me say a word now about liquid welfare. So what is liquid welfare? Liquid welfare is, we're going to define the value of an allocation as the maximum amount that the agent would be willing to spend to get that allocation. Okay, so in this case, in this particular case where you have hard budgets, this is just the minimum of the declared like maximum bids and the budget constraint. Okay, so in the case where one agent has a really low budget, in some sense, it's easier to get good liquid welfare because their budget constraint is going to bind earlier. Now, okay, why do we care about this? So certainly this has been used quite a bit in the context of budget constraints. But I want to say in this particular setting with the auto bidders, I think this is particularly appropriate. Remember, the auto bidders themselves don't have utilities. They just have these mandates from the advertisers. So saying, subject to these constraints on how much I'm willing to spend for different things, please maximize my value. Liquid welfare is precisely saying, maximize the amount that the individuals are willing to spend for what they received. And so in some sense, I want to think of liquid welfare as how well the auto bidders jointly satisfied the mandates that came to them from the advertisers. Okay. Good. Okay. So this seems very promising. Okay, so we're basically saying, hey, what we should do, we should run a second price auction in the background. We should run these auto bidders at equilibrium. We get this 2 approximation. Fantastic. Except it turns out that finding a Nash equilibrium in this game is computationally hard. Okay, there's this PPA hardness result. Now, sometimes in price of anarchy results, we sort of take the hardness and sort of like shove it under the rug a little bit. But I want to note in this context, it's actually really central. Okay, so the whole point of doing auto bidders in the first place was that sort of bidding in these auctions is hard, and we wanted to sort of push this off to the platform or to sort of do things on our behalf, right? But if it turns out that we can't have that the bidders themselves are converging to equilibrium, then it's hard to think about what they're actually going to do in practice when they're, say, doing these learning algorithms. Okay, so we don't want to rely on the equilibrium results to argue that we're going to get good outcomes if we don't believe that necessarily they're going to find equilibrium when they're running these learning methods. So now, okay, halfway through the talk, I can now actually get to our results in slightly more formality. Okay, so what we're going to argue is that you can preserve that 2 approximation result without relying on this convergence to equilibrium. Okay, so there is a sort of very simple adaptive pacing algorithm the auto bidders can do, such that when they run simultaneously, you're going to get at least half of the expected optimum in terms of liquid welfare. Okay, this is going to be robust, like it works for a class of different options. It doesn't rely on the underlying option to be a second price. It can be GSP or first price or whatever. This would still work. And the second result is just saying that we're not, doing something funny. The auto bidders, this method actually is a good way to run an auto bidder in the sense that it actually like solves the mandate for an individual advertiser, right? You get vanishing regret in like a stochastic environment. Okay, so good. Okay, I've talked quite a bit about this already actually, but just to put it all in one place, lots of work on budget pacing. A lot of the work has looked at things like conditions under which you get convergence, these equilibria, and what those equilibria look like for both sort of first price and second price auctions under the hood, and sort of incentives behind the back. I want to give a particular shout out to this Borgs et al. Paper. Actually, let me do this pointer. Yeah, this Borgs et al. Paper, which sort of showed convergence for when the underlying auction is a first price auction for dynamics that's similar to the one I'm going to describe, but is a little bit different. And this was sort of well ahead of its time. It was quite a while before the rest of the literature started looking at these questions as well. Again, we're going to be looking at our metric of liquid welfare and sort of trying to extend it beyond equilibrium analysis. I want to compare this. There's a literature that's recent and like really exploding right now, which is looking at ways to do auto bidders in different types of mandates and formats, right? So we're focusing on, I'm giving you these budgets and max bids. Please, maximize value. You could also add in things like ROI constraints and ROI targets and ask like, how do I solve the learning problem? So there's a huge literature on that. We're not going that way. And in particular, comparing, what can I do like with a learning algorithm internally versus just giving the advertisers themselves enough information to solve this problem themselves. For example, these dashboard mechanisms. And the other thing I want to compare against is the sort of the RL literature, the reinforcement learning literature on how you would actually do the regret minimization task itself. Right, so this is like bandit problems with constraints, like bandits with knapsacks. So you can frame all of this as like a bandit with knapsacks problem, where the budget is sort of constraining what you can spend over the course of the entire learning period. And so there are much more interesting and fancier things you can do than what we're doing in this paper, and that get sort of better regret guarantees. So in some sense, what we're doing is sort of a more straightforward learning method that gets vanishing regret, though not optimal regret rates, but nevertheless has this additional property that you get good outcomes when they're running simultaneously. Okay, so now in the remainder of the time, what I want to do is just run through the different parts of this description of the results and sort of explain what's going on. Maybe this is a good time, now that I've sort of actually described the results, Sergio, to come back to your original question about the implication of the distribution being the same across rounds. So I want to just make sure that that's been clarified, that I can handle things like my demographic is changing over time.
Well, not exactly. I'm still not happy, but let's leave it. It's not important.
Okay. Okay. Sounds good.
Anyway, you know, I belong to the people that already go with a cane in your picture, you know.
Okay, perfect. Good. So let me talk about, first of all, what I mean by this pacing algorithm. So what is the pacing algorithm we're talking about? So this is, as I mentioned, this is a method that's been studied before. It came out of Basar 2017, and it works as follows. I'm going to start by saying, and remember, this is from the perspective of a single auto bidder. I'm going to initialize my mu to be 1, right? Which means I'm going to start by bidding my value. And then in each round, I'm just going to say, it's a pacing method. I'm going to bid max value divided by mu. There's subscript i's everywhere here, but I'm excluding them because it's just a single issue here. And then I'm going to send that bid to the auction. I'm going to observe my payment. Okay. Actually, I don't even care what the outcome was at all. I just observe the payment. And now I'm going to update my mu in a way that depends on how that payment relates to a target. And that target is just the average spend rate that I would like to observe in order to hit my budget. Okay, so this is just my budget over time. I'm going to call this rho. I'm going to take that and multiply it by a learning rate. Spoiler, like most of these learning methods, like you want to set this to something like 1 over root t. It's actually not so important for the purposes of this talk. And you know, in case you're like me and you always have trouble with signs, I just want to point out this is going in somehow like the right direction, right? So it's basically saying if I spent too much, I should set mu in the way that causes my bid to be lower in the future and vice versa. Okay, so I'm just locally and sort of greedily tuning to try to hit this target rate. And I want to point out this is basically just trying to implement something like this picture I showed earlier, right? So in some sense, you can imagine all these arrows are pointing in the bias, right? So like, remember, it's a stochastic. So each individual impression is random. It could be that I'm spending more on average, but I actually observe that I spent less, like maybe I lost. So my actual update rule could be quite noisy, but on average, I'll sort of be pointing in the right direction, right? So there's like a connection to like stochastic gradient descent here. So on average, I'm pointing in the right direction. And so this method is attempting to try to follow this sort of pseudo gradient that's sort of drawn here. Okay, some details. Remember, I'm not allowed to set mu less than 1, so I'll just cap at 1 if this rule tells me to go less. And the other detail is that, as Sergio pointed out at the beginning, I might run out of budget early, in which case if I'm run out of budget, then I have to bid 0. Okay, well, it's going to turn out that when I use this method, I'm not going to run out of budget too early, as long as the environment is relatively nicely behaved. Okay, good. So this is the method that the auto bidders are using to tune bids. Any questions about this? Okay. Good. So now, what do I mean by class of options?
Wait.
Yeah.
I do have a question. Why is your target B over T and not, because that's payment. Payment is, say, 0 if you didn't get the good and whatever the value of the good if you got it. Why don't you aim higher? Because it may well be, suppose that we are in the example where you are bidding half. I mean, I was winning in the 150. In the example you had, I think that I was spending 50, but I was gaining 100. No, am I wrong? I was no, not 100, 200. Sorry, I was getting $200. So why am I aiming at B over T and not at? Isn't that an undershooting by?
So good. So this is exactly somehow the point, is that this actually is independent of the values. And so in that example, it's true, you're getting 200, which is great. It turns out that the optimal way to get that value is to set a bid such that the payment sort of exactly hits the budget. So we know that if our payments are sort of hitting the budget, then we did as well as we could have done with respect to value. Now, I don't know how high that value is, and this method isn't depending on it. It's just saying that I know the right thing to do is to try to hit the right spending rate. And so we're going to try to do that. So in this case, it's basically just saying I want my payments to match the $50. And it's not saying I'm trying to get the values to match the $200. If that makes sense. I'm not sure if that addressed the question.
Brendan, can I continue asking about it? Is B here only my own budget or everyone's budget combined? Because
It's only my own budget.
because somehow I imagine that let's say if we all know that all impressions are identical, then you would imagine that the average price, the price of every impression should be the total budget divided by T. And yet you're bidding much lower here.
Yeah. So it's what's interesting. So what's going to end up happening is that, so suppose that there's that situation where our budgets are the same and the values are the same. Then what's going to end up happening is I want to win at a certain rate to get my budget satisfied, right? So what I'd like to have happen is to exactly hit my budget in retrospect over the course of the T rounds. So what I would expect to happen in this case is that, maybe we're underbidding and I lose, right? Oh, okay, I'm going to increase my bid because of this dynamics. And now someone else loses, and so they increase their bid as well. And so we would expect to sort of chase ourselves up. But what's going to happen is suppose that there's 3 agents and we would all hit our targets if we each won a third of what's available. Then what it would expect is that when I win, I actually overspent my target by quite a bit, right? It's sort of spiky. So I win. Oh, I overspent by quite a bit. Okay, I'm going to drop my bid a lot. And now it's going to take me a couple of rounds to build back up to get back to where I were. So what you would expect in the dynamics is sort of I'd win. Okay, I drop down. Now I lose, so I go up. I lose, so I go up. Oh, I won. Okay, I drop down. And so you're going to get this sort of funny monkeying around the equilibrium pole. Does that intuition make sense? It's basically we're saying something like what's going on in the picture here.
Yes, I mean the problem is that my intuition is that suppose the values are extremely high, and then everyone will just spend their budget, and suppose that all item impressions are completely equivalent for everyone. Mm-hmm. Then the right value, the right price for each item should be the total budget divided by T, right? So this should be intuitively, this is what all of them should have in mind, because if I know that, let's say I'm 1/3 of the total budget, then that's the price I should buy impressions at, right? And
okay, good. So it's important that these budgets are binding across everyone. So even if the values are astronomically high, if the budgets are low, the fact that the values are very high is in some sense immaterial. Right. The equilibrium prices are still going to be quite low. Now, it's true that the prices are going to be such that everyone's budget is exhausted at the end of the day. But if everyone's spending their budget at a basically equal rates over the course of the day, it's still the case from my perspective as an individual that my average spending rate over time, my personal average spending rate over time, is going to be basically my budget over T. It's just that everyone is spending at that rate. And so the total spending rate is like the sum of the budgets over time.
Okay, thanks.
Cool.
Just to make sure, what is PT? What do you call payment? What's payment?
Well, this is the total amount that the agent had to pay. So
that's mu T times VT.
That's how much they bid. So VT over mu T is how much the agent bid.
Oh, so in the second price auction is, say, the second, whatever the second bid was. That's what you mean?
Exactly.
If he won, and if not, it's 0.
Yes. Correct.
Okay. So it's the... Okay.
Okay. All right, let me speed up a little. I promised that this works for a bunch of different auction formats. Let me say just briefly what the conditions are that I need. What I want is that my underlying auction is what's called a core auction, right? Generates auctions in the core, which if you're not familiar, the way this is normally described is saying that there's no coalition of the bidders and possibly the seller that could jointly deviate and implement some other outcome that would be better for them. In terms of this particular simple auction setup, what this basically means is people don't pay more than their bid for what they got, right? So no one has to pay more than their declared value for what they obtained. And secondly, there's this condition that basically says there's no set of bidders. For any set of bidders, A, I can look at the declared value those bidders got, and I can look at the difference between that and any other outcome those bidders could have gotten. And that difference has to be covered by the revenue that the auction received from others. Okay, so if you've worked on things like smoothness or like balanced prices and profit inequalities or something, this sort of condition should look familiar. This is like a charging sort of condition. And just to give some intuition, if I took A to be the set of all bidders, this basically just says the auction declares maximizes declared welfare. If I took A to be all bidders minus one, basically this just says that every agent payment should be at least their VCG payment. And it gives some, but it has some extra constraints as well that actually says the payment should be in general higher than the VCG payments. And I just want to point out, first price auctions, second price auctions, GSP auctions, they all satisfy this condition. I need another technical condition, which is that the auction satisfies what I call monotone bang per buck, which is basically as your bid goes up, the value, the allocation you're getting per unit of money spent is weekly going down. Okay, so give some intuition, like first price auctions have this property because as my bid goes up, I'm paying more, but getting the same amount. Second price auctions have this property. Basically, this is just to rule out sort of weird scenarios where, you know, this slack between first and second price, maybe I have some auction that like does something funny and non-monotone as I move my bid up or down. Okay. And so that's the class of auctions. Okay, what do I want to do? I'm going to just very briefly mention why it is that this auction format works. This auto bidder method works for the single agent auction, just because it feels like that would help with building intuition. So the theorem here is that from the perspective of any individual bidder, I'm getting basically a low regret result with respect to like the optimal value I could have obtained in hindsight over the course of running this system, running this auto bidder method. And I want to, because this is now like a single agent result, I want to imagine this in like a stochastic environment. Okay, so I want to think of it as like each round, the advertiser's value and the bids of the others are being drawn from some distribution, right, that's joint. And so the way to think about this is, let's imagine that like all the other auto bidders have their mu values fixed. So they've all like converged. And now I'm just looking at the perspective of a single auto bidder that now enters into the market, right? And everyone else is converged. Okay, so this is like a large market, like mean field type of solution concept. And I basically want to say in that sort of environment, this auto bidder is going to perform well. My benchmark is going to be an ex-ante benchmark, which basically says, imagine that you were bidding such that you exactly hit your revenue target and expectation. I'm going to say, how much value would I then obtain per round on average? Okay, and this is an upper bound on how well the best bidding method could have done in hindsight, in expectation. When you actually want to write down a proof for this, you basically do it by saying like, oh, I can interpret this update rule as like following the gradient of some, you know, special dual function that I've designed precisely for that purpose. Then I invoke stochastic gradient descent and connect that to the value that the agents obtain. This is precisely what's done in Balsara-Gur, for example, for the case of second price auction, where you actually have independence across the values of the individuals. So in some sense, what we're doing here is extending this to the broader class of auctions in a broader setting. But I'm not going to show that. I just want to give some intuition about what's happening. So imagine I plot out for different values of mu, what would be my expected per round spend if I just use that mu every round? Okay, remember this is decreasing because higher mu means lower bids. So imagine every bid, I decrease my bid, my max bid by half. I'm going to spend a certain amount in expectation over all the rounds. Okay, now our benchmark is precisely the mu that causes me to spend my budget exactly if I did this, right? Which means my per round spend is rho. And now we're saying is, let's suppose that I had a spend that was a little bit off from rho. Okay, suppose that I'm wanting to spend on average a certain amount per round. Maybe I'm a little bit off. I can then project that into like a ball around mu star, right? And these are the mu's that are such that if I did that every round, my spend would be approximately what I want it to be. And the thing is we don't get a convergence result precisely because this S could actually be quite big. It could be quite a big ball around mu star, depending on how this function looks. But the claim is that our dynamics is almost always going to be in the set S. And this just follows from interpreting the update rule, right? So remember, what we're going to do is we're going to take our mu and update it by epsilon times the difference between my actual spend and my target, which means my expected move is going to be the expected difference between rho and my target. If I'm outside S, that expectation is quite large. Okay, just by definition, it's going to be at least delta. So basically, it means every time I'm outside S, there's like a bias, there's a force pushing me towards S because my spend is different than what I think it's going to be. And so basically, I want to think of it as I've got a random walk on the x-axis, and that walk is biased towards mu star always. And so then the last step is to show that if I'm in S most of the time, then my value is going to be good. All right, so I could plot, on the left is my spend, on the right is my value, right? How much value am I getting if I bid this mu? And I just want to, and the idea is that the value is actually going to be close, and the argument is different based on whether I'm overspending or underspending, right? So if I'm overspending, if my mu is too low, which means my bidders are too high, then what's going to happen is I'm going to run out of budget too early. But as long as the amount that I'm overspending is within like a delta, then I'm going to not overspend too early. Okay, and so the value I obtain is going to be at least higher. And here's, when I'm overspending, it means I'm getting more value per round, but I'm spending too much. So if I run out like something like t times 1 minus delta, I'm going to get something like a 1 minus delta of the value. More interesting is the case where I underspend, right? So if I'm spending too little every round, my budget constraint isn't going to bind, but I'm getting less value per round. And here's where we use one of our auction conditions, which is that because my bang per buck is only going up as my bids go down, if I'm spending my budget like minus some delta, it means my value is also going down by almost like a factor delta. Okay, so all of this is basically establishing this intuition, which is that in this sort of scenario, bidding in order to hit my budget target is also going to maximize my value. Okay, good. So that's that. Let me now just, again, like super briefly talk about what goes into proving this main theorem, which is that now I want to say, suppose I'm running these auto bidders simultaneously, then my expected liquid welfare is going to be at least half of the expected optimum. Okay, so what do I mean by this? So now if I'm running these auto bidders, there's some allocation that's going to be obtained. And that allocation is like a random variable. So it's like every round t, I get some amount xit, right? And it's maybe if it's a single, like if we think of it as an indivisible auction, it's just did I win or lose? Okay, and we're basically want to say that the expected welfare of this x over all sources of randomness is at least half of the expected optimum, which in math just says this. Okay, I want that the expectation of the sum over all agents of the minimum of their budgets and the total declared value they obtain. Remember this liquid welfare definition, that the min is at the level of an individual agent, is at least half of the expected optimum where I'm looking at like in hindsight. So I'm saying over the actual realization of all the values, look now at hindsight of like what would be the allocation that would have maximized this liquid welfare over that realization. Okay, so to understand this, I want to, again, so as before, we think of this mu as sort of evolving over time, right? So I'm an auto bidder, I'm tuning by some fraction. Sometimes I'm at 1, right? Which means I'm not shading at all. And then sometimes based on sort of what I've seen, maybe I'll start like shading more aggressively. And so I do this sort of walk away from 1. I start shading. So here I'm bidding quite low. And then eventually I decide, oh, I'm going to start bidding high again, and so on. Okay. So this is some random process. what I want to look at is like these maximal intervals where I started shading, did some stuff, and then eventually I stopped shading. I'm going to call this an epoch. And the main technical lemma is that for this particular dynamics, there's this nice relationship between these epochs and how much I spent. So I claim that if there's some epoch, some shaded region, this T1, T2, then the total amount that the auto bidder spent over that region is basically the target spend rate times the length of time. Okay, so if I, if this went off for like 100 rounds, then I spent basically 100 times rho.
But that's assuming that the epoch is large enough that lots of large numbers kick in, right? Or not?
No, actually, interestingly, no. So this actually holds pointwise. It holds pointwise, and this is where
even for one period, you mean? Or for one period doesn't say much, but
for one period doesn't say much. There's this little extra a bit here that I'll talk about in a second. But so for one period, it's actually a little bit funny, but for 2 periods or more, yes. And this is basically just a telescoping sum. So the basic idea is, remember, I shade more when I underspend, when I overspend, and I shade less when I overspend, right? So it's like if my mu goes up, it's because I spent too much. And then my mu goes down when I spend too little. And the particular format of the dynamics is such that these forces exactly balance each other. So if I start at a certain point, I go off for a while, and then I come back, it means that the amount I overspent exactly balances the amount I underspent. Okay. Now, there's a little detail.
That's why you need to run away from periods where the constraint 1 kicks in.
Yes.
That's what kills the balancing act. Yeah.
Exactly. Good. But now this actually is making our life really easy, right? So if, for example, my trace looks like what I've drawn here, where most of my time is shaded, I'm basically done, right? Because it means that my total spend was at least all of the shaded time space times my rho. So if, say, I'm away from 1 at least half the time, it means that in total I spent at least half my budget. But I know that my budget is an upper bound on how much my liquid welfare could be. Right, so this would anyway give us our 2 approximation. Okay, so actually the interesting case is exactly this sort of scenario where actually I'm bidding 1 most of the time. And I'm basically out of time. So I think all I'll say here is that if I'm in a scenario where I'm bidding 1 most of the time, things work out well because of analysis that we typically do for things like smoothness or price of anarchy for auctions. Okay, so the idea is that if I'm in a scenario where an advertiser, like an auto bidder, is bidding 1 most of the time, it means they're bidding their value most of the time, which means that either they're winning or they're losing, but someone else had to pay a lot in order to beat them. Okay, so this is exactly, let me skip this. This is exactly this core auction property. So basically we'll say something like, either I'm winning, in which case I'm happy, I'm getting high value, or I'm losing, but then by the core auction property, or more generally like just things we know about first and second price auctions, if I'm losing, it means someone else was paying quite a lot in order to cause me to lose. And so I can charge any value I lost to the payment of others. And because liquid welfare is precisely the maximum amount that people are willing to pay, if someone paid something, then that's a real contribution to liquid welfare. And so this charging makes sense. So that's a bit of a super fast high level, but just give us a flavor of what's going on. And I don't have time to go through this, but I want to just mention this 2 approximation is tight. Okay, so even just looking at like Nash equilibrium, there are examples where you can't get better than a 2 approximation to liquid welfare. And I can talk about that afterwards if people have questions about it. So let me just sum up. This is all about automated bidders, right? So this is basically algorithmic campaign manager. You have these advertisers in the online auctions who basically give instructions, they give mandates to these algorithms who then bid on their behalf. And what I want to talk about today was this adaptive multiplicative bid pacing, which is this particularly simple way to adjust bids over time. And it turns out that when when the auto bidders simultaneously do this, they might not converge to an equilibrium, but you still get at least half of the optimal total willingness to pay, which is liquid welfare. The optimization is local, it's very simple, it's robust to details in the underlying auction, and still gives you strong individual performance guarantees. bunch of stuff to do next, not listed here, but I mean, you could ask whether similar properties hold for more complicated RL methods as well that give better regret guarantees. You could also ask about like these different formats of auto bidders. Like what if I threw extra constraints in as well, or modified the meaning of the language of like how the advertiser and the auto bidder talk to each other? You could ask whether similar results still hold. And also there's interesting questions here around just what happens if I talk about things from the advertiser's perspective as well. All right, so what actually happens when the advertisers are strategically thinking about what the auto bidders are going to do and then respond themselves? And we sort of have partial answers for this when you have like second price auctions as the underlying auction in particular, but sort of more generally, I think there's a lot of work still to do in terms of understanding the game between the auction, the auto bidders, and the advertisers sort of all together. Great, so that's all I had. Thank you very much.